we can go from the angular momentum of a single particle defined for taking the angular momentum about some point in space. You use that same point in space, you can get the angular momentum for a whole system of particles or a continuous object, just as you would for the total momentum of an object. So conceptually, if I want the total angular momentum of a system, I just add together all of the angular momentum of the individual parts. And then we have an understanding of what a net force does. Net force changes the momentum of a system, and a net torque changes the angular momentum of a system. If you have an isolated system, so there's no net force, then its linear momentum is constant. And there's no net torque, then its angular momentum is constant. And then one of my favorite XKCD cartoons of having a sweet thought applied in terms of physics. So a couple questions. Make sure we have a good understanding of conservation of angular momentums. This is a classic demonstration. Physics student is on a rotating stool that has very little friction in its rotating mechanism. And he starts with some masses at arm's length, so a long way from his axis of rotation. And in that situation, when his arms outstretched, he sets spinning. Okay? And by applying a torque briefly, and then while Joe is spinning, he pulls those dumbbells in closer and closer to his body, and you observe that he will spin around faster, right? So why does his speed increase? Which of those is the correct reasoning? So read them through, think them through, talk it over, and then we'll go over the answer together. All right, so bring the dumbbells inward. Joe is decreasing the moment of inertia. Therefore, he has to increase his angular speed. L is constant, and that L is equal to I times omega. And so reducing his rotational inertia means I gets smaller, and to compensate for that, omega has to become larger, so he spins faster. No change in angular momentum, it's angular momentum being conserved. All right, and then more of an astronomy setting. The star is rotating about an axis that passes through its center, and that star dies. The balance between the inward force of gravity and the outward pressure from nuclear processes is no longer present. So nuclear fusion makes the core hot, and that hot plasma exerts pressure. So the star will collapse inward, its radius decreases with time. Which one of the following choices best describes what happens as the star collapses? So read through those possibilities, talk it over with your physics neighbor, and then we'll go over the answer together. So as the star collapses, the angular momentum of the star is going to remain constant. So the rotational inertia decreases, angular speed increases, but it's maintaining the same amount of angular momentum because it's an isolated system. The sum of the torques exerted on the star is going to be zero. It's not actually any different in your reasoning than Joe sitting on the stool, which is one of the nice things about physics. You see the same physics regardless of the system, be it a star or a person.